Okay, in this video we are going to see how to make the Laplace transform of functions that are that have some translation or have a shift. Usually a shift on the right. Okay, now imagine this. Now in the previously we saw the translation on the S domain, but that is another thing. That is the translation on the S domain. With the exponential here, it happens that it is a shift in the function, but in the S domain. Now, here we are going to see what happens if the function here, this is the function f of t, we can calculate the Laplace transform of f of t, that we get capital F of s, and here you have the definition of the Laplace transform. Okay, now, what happens if you push to the right the function? Meaning that this function goes to the right, like this. Okay, now, because the Laplace transform definition starts on 0, okay? So the function of f of t, we don't care what is, or we don't care what happens before the time is equal to 0, in the negative part, okay? So if we shift this function, we don't know what happens here, right? Now, because we don't know what happens here, we have to make sure that this is equal to 0, all right? Okay, so that makes a complication, because in reality, when you shift a function to the positive side, if you shift it to that, you are going to get something like this. But you are not sure, because it is actually a void, emptiness before that. So if you shift it to the right, you have to make sure that you don't include this part on the Laplace transform. Okay, so that is why it's a little bit different. Okay, now, if you happen to have 0 here, so that makes that it is actually the step function, very similar to the step function 0 and then a and then equal to 1. So this is the u of t minus a. Okay, now in reality, to make this equal to 0, what you have to do when you shift to the right, what you have to do is f of t minus a, u of t minus a. So this is the shifted function, or translation function. Translation function. Again, why you have to add the u of t minus a? Because you have to make this part 0. Okay? Now, because you have a multiplication here, 0 times anything of the function is going to become 0. Alright? And then 1 times anything equal to anything. So 1 times the function is actually the function. So when you shift to the right, you are making this part 0. And how you make it 0? With a step function in a multiplication. Alright? Okay, so what we have to do right now is to make the Laplace transform of this function, the Laplace transform of f of t minus a, u of t minus a. Alright? Okay, let's do it by definition. The definition here is the integral from 0 to infinity, the exponential minus st, and then f of t minus a, u of t minus a, differential of t. Like in the previous videos, what we are going to do is split the integral in two parts. The first part here, and then the second part here. Okay, so it's going to be the integral from 0 to a, here the value of a, exponential minus st, and then f of t minus a. What is the value of the step function on this part? Well, it is 0, differential of t, and then plus the other part of the integral from a to infinite, exponential minus st, and then here is f of t minus a, and then 1, differential of 1. Remember that it is 0 and then becomes 1. So it is 0 and then becomes 1. Now, I don't care about this part of the integral because it is 0. The only that remains is that part. Okay. How to solve that integral? What we are going to do here is a variable change. I'm going to make w equal to t minus a. So t is equal to w plus a. You can see, and just clear the t. And then differential of w is equal to differential of t, because the a happens to be a constant. It doesn't move, it is fixed there. Okay, so let's see what happens if we make we change that integral. Exponential of minus s, and the t happens to be w plus a. F of t minus a happens to be w. Differential of t happens to be differential of w. Alright? Now be careful here, because you also have to change the limits. So t is equal to a and t is equal to infinite. Now here we have to calculate what is the value of w, because here the integral is as a function of the time. Now here is a function of w, so we have to make the limits. Now, what is the formula? Well, here is the formula. If t happens to be a minus a, it is 0, and then if t happens to be infinite minus a is still infinite. Alright? Okay, so on this integral, what you get is 0 to infinite exponential minus sw times exponential minus sa. If we do the multiplication, and then f of w, differential of w. Okay, now let's do another variable change. I'm going to make w equal to t. Because it is equal to the t, then it's going to be integral from 0 to infinite, because it's the same variable. Sorry, I forgot here. I'm going to take outside what is constant, and what is constant? This part is constant, and it is in a multiplication. Okay, so it's going to be exponential minus as, exponential of minus as, integral from 0 to infinite. If we do the variable change, exponential minus st, and then f of t, differential of t. Now, have we seen this before? Yes, the answer is yes. We have seen that before. It is actually the same formula from 0 to infinite, exponential minus st, f of t, differential of t. So this is actually the Laplace transform of f of t. So this is the Laplace transform of f of t. Okay, so from where did we start? We started from here. We started here, all this thing, and then over here. Okay, so what we get is, we started with the Laplace transform of f of t minus a, u of t minus a, and that is equal to exponential minus as, the Laplace transform of f of t, which is the same as writing the f of s, right? Okay, now, this is a very useful formula, because from here we can also write the Laplace inverse. The Laplace inverse of the exponential minus as, f of s, is equal to f of t minus a, u of t minus a. And this is very important formula that we are going to use. Next video we are going to see how to use this formula, okay? See you.